in the previous video, we have seen that the probability density for the position and velocity of a Brownian particle is governed by this partial differential equation called the Kramers equation. Then the natural question is whether there is an equation of motion that corresponds to the Kramers equation, and the answer is yes, and it's called the Langevin equation. And so anyway, this is the Kramers equation. And actually, as for this part, which comes from Liouville's equation, we already know the corresponding equation of motion, because of course, Liouville's equation came from the Hamilton equation or the Newton equation. So actually, if you look at this carefully, not very carefully, if you simply look at this, you see that this corresponds to this equation. Actually, this is only the definition of v, velocity, and this one corresponds to this equation. This is the Newton's equation. Okay, so we already know the answer for this part. But actually, this part is new because this part came from the effect of collisions between the Brownian particle and bunch of water molecules. And so I will show you the answer from now on, and we will find that this first part actually corresponds to very simple equation of motion that everybody learned in the freshman physics class. And this is the equation of motion for a resisted motion. So there is a resistance which is proportional to the velocity. Okay. So actually, interestingly, this is a deterministic equation. So actually, this is also a Newton equation. And this part is different. And actually, if you look only at this part, you will find that this looks like the diffusion equation, but for V. So this is nothing but the diffusion equation for V. And this is different, and we will show that this the equation motion corresponding to this diffusion, like behavior, is this one. This is not a deterministic equation, but it is an equation of motion with a random force here. Okay, so anyway, these are the answers. So in the rest, I will show you that these things actually give this and this. But actually, we have to be careful about the definition of psi. Okay, so let me start with easier one, this resisted motion. So now I start from the answer. So this is the equation of motion for the resisted motion, and you can solve it. This is a general equation. And now, so this means that if this is v-axis, so if v is v naught at time 0, then it is e to the minus gamma over mt times v naught at time t. And again, this becomes this too. So this width of this interval, if its width is delta v here, and here the width becomes delta v times e to the minus this same factor. Okay. Now I write down the law of probability conservation. So suppose that delta v is small, and so the probability that your v is in this interval at time 0 is given by this. This is probability density, and I omitted x here, but probably x is here, but I omitted. So this is probability density, and this is the width. So this is the probability that your v is within this interval, and this interval just evolves into this. So the probability that you are in this interval is, this is the probability density at time t times this is the width of the interval. And of course, they must be the same because of the probability conservation. Okay, so this means that this part, which I denoted as star, is independent of t. So I will differentiate this with t, and you have to be careful. There are t here, here, here. So first of all, if I differentiate with this t, what you get is this. I will plug this into v after everything, and I differentiate here. And as for this one, you get this. And as for, if we differentiate this t, you get this. Okay, and this is 0 all the time. And so you can forget about this e to the minus. And so this sums up to be 0. So you will find that this is equal to the sum of this and this. And this is, of course, the desired equation. Okay, so you get this, and this corresponds to this. Oh, no, this one. Okay, now that was an easy one, and I will now discuss this diffusive-like behavior and the equation motion with a random force. Okay, and now for some technical reason, again, I will treat time as a discrete variable, and I assume that t is always an integer times epsilon, which is a fixed, very small constant. And in this case, we need to do this because otherwise the mathematics will become too complicated. Okay, so now everything, time is discrete, and now velocity is continuous. And now this is the equation of motion for the velocity that I write down. And of course, this is basically the time derivative in this discrete time world. So this is m times v dot. And it must be equal to the force which is acting on the Brownian particle. And I would say that this force is random. So since this is a random variable, I put hat here. And since this is random, v also becomes quickly random, so I also put hat here. Okay, so this tells you that, oh, okay, this can be rewritten in this way. So this tells you that when time evolves from t to t plus epsilon, then you choose a random variable psi and you add this to v, and this, you repeat this. Okay, and what is this psi? Well, this is a random variable, and we prepare this random variable for each t. Okay, where n is integer, and we declare that when t and t prime are not the same, these are independent. Okay, and as for this single random variable psi, we define that the probability density that this takes value psi in R is given by this Gaussian probability distribution. Okay, and so this is just a standard Gaussian, and actually I already fine-tuned everything. I know the answer, so I fine-tuned everything so that to get the correct answer. Okay, and this is just the basic property of the Gaussian integral. This is normalized, and the moment of this psi is of course 0 because it's everything is an odd function, and this integration can be easily obtained by doing integration by part. So you get this. In terms of this psi, first of all, from this, you see that the average of this random quantity psi is 0. And if you consider this kind of correlation, then when n and m are not the same, then because of this independence and this, we see that this average is 0. And when n and m are equal, then from this, you see that this is given by this. Okay, so I use this double bracket because this is a kind of path average, time-dependent average. Okay, so this is the basic property. So this is our basic equation of motion, which involves random quantity, and this random quantity is precisely described here. Okay, now we can think about the master equation for the probability density for V. Now V is governed by this stochastic process. Okay, you pick V at time t, and then you pick this initial this random quantity, and you add it to this V to get the new V. So this is a corresponding master equation. So again, this is a difference of the probability densities, and here this is the escape part. Okay, your velocity is v at time t, and now it escapes. But this is so it escapes to t plus epsilon m over psi. But you know, and you sum up, you integrate over this psi. And this is a weight. But by what normalization, this is 1. Since the Gaussian is normalized, this is just 1. Okay. And now this is coming in part. So your v is was this at time t, and you add epsilon over m psi, and it jumps into v. Okay, and this is a weight. Okay, so since this is 1, you can rewrite this like this. Okay, and now since epsilon should be small, you expand this, you Taylor expand this. And the Ross order vanished, and this is a first order, this is a second order, and you're going to perform the from Gaussian integrals. And of course, here you get 0, and from xi squared, you get this factor. So this is what you get. And you see that this is order epsilon, and this is small order epsilon. Okay. And now you divide everything by epsilon to get this, this, and this. And if you let epsilon go to 0, this becomes this partial differential equation, which has the form of diffusion equation. And actually, this is what we wanted. Where were we? Yeah, this one. So we got this. We got this. Okay, so anyway, we got all the parts. We could derive all the parts of Cramer's equation, but actually our interest was in the equation of motion. So we have to discuss the continuum limit, epsilon goes to 0 limit of the equation of motion, and this is actually a non-trivial part. Okay, so this is the equation of motion with discrete time, and I want to take this epsilon going to 0 limit. And of course, this should become this time derivative. And so I write the continuum limit of this psi as this. Okay, I still do not know what this is, but I simply write it like this. And actually here, these are all discrete time world, and these are in continuous time world. Okay, and in this discrete time world, we know that the correlation function of 2 psi is given by this. And especially when n and m are not the same, and then this is 0. From this, you'll see that the correlation function of psi t and psi s when s equal not t must be 0. Okay? This is just a natural continuum limit. And also from this, you find that if you multiply this by epsilon and add over m, you get 2 gamma over beta, something finite. And in the continuum limit, this summation naturally becomes the Riemannian integral, and you get this. So NE is T and ME is S, but you're summing over M with this, so this becomes the integration over S. So you see that this is equal to this. So we have these two. This correlation function is 0 when s is not the same as t, but if you integrate over s, you get this finite quantity. This means that this correlation function must be something singular, which is a delta function of t minus s with this coefficient. And also, since the expectation value of xi itself is 0, we also see this. Okay, so this shows that this random quantity xi is a bit strange quantity. And in physics, this is known as the Gaussian white noise, and people are happy about this definition. But if you go to mathematics community, it's not very easy to make a precise meaning of this kind of quantity. Of course, I think you can do it, but you have to sort of extend the mathematical terminologies. But you can, the life is better if you consider this quantity, which is basically the sum or the integration of psi. And if you take and if you consider the epsilon going to 0 limit of this thing, and then you get something called a Wiener measure, and which is rather well-defined measure, which is continuous in t. So usually mathematicians treat this quantity, W, the Wiener measure, Wiener process, rather than xi itself. But here I don't care, and I do as physicists usually do. Okay. And by the way, this equation, this relation is sometimes called the fluctuation dissipation relation of the second kind, to emphasize that this determines the magnitude of this fluctuation noise random quantity xi in terms of this coefficient gamma in beta. Okay, and beta is of course the inverse temperature, has a physical meaning, and gamma also has a physical meaning as the coefficient for this resisted motion. Okay. Oh, oops, it's here. Okay. So it has a clear meaning as a coefficient here. And it is rather interesting that the magnitude of noise is related precisely to this coefficient gamma. But actually this is necessary because if you recall the origin of this random force and this resisted motion, you recall that everything came from this collision of water molecules to this Brownian particle. So the same origin led to two different terms. So of course, these two different terms must be related precisely with each other. And this relation is expressed in this equation for sign. So people call it this way. Okay, so now we know what this sign is basically. And so now we can write down the final answer. To sum up everything, the Cramer's equation with this deterministic part and this part coming from collisions with water molecules is equivalent to this equation, which is called the Langevin equation. And okay, and this is the main part. It says that the m times the acceleration, but this is already random quantity acceleration is equal to f. This is a deterministic force when the particle is at x, and this is again deterministic resistance. What is the correct word? I don't know. And this is the random force, and this is a Gaussian white noise satisfying these relations. Okay, so what we did, we started from fluctuation theorem time consideration, and we finally reached this Langevin equation. Okay. Oh, and actually, I have to say that this kind of equation of motion is usually called a stochastic differential equation, and there is a precise mathematics for treating this. But here in this lecture, I'm not going into details of mathematical theory of stochastic differential equation. And then in the next video, which will be the final video of this lecture, I will use the Langevin equation to discuss Einstein's theory of Brownian motion.